as we head towards the balance of this chapter and finishing up this chapter, I know that the assignment is due on the couple days coming up, I think the 7th. So you can start looking at that. But as we finish up, we've got a couple more items to talk about when we look at gases, okay? And so we learned previously, up to this point in time, that the gases follow laws and behaviors, right? And there were lots of guys that had names that related those different things that went together, okay? And you probably should know the name and what the association is. Who did pressure versus volume, that relationship? Who did temperature and volume, okay? But ultimately, it came to a equation called the ideal gas equation that said the pressure times the volume is equal to the moles times an R constant times temperature. Now that R constant had a number, a really strange number. It was 0.08206, but this is where the strange part comes in. It's units. It is a liter times an atmosphere divided by a mole Kelvin. And so R is defined in those terms, those particular units. And so when we find and solve for problems, we have to be in those units. Now, what we're going to discover later is that there are more than one R. In actuality, there's somewhere in 10, 12 R's. We will learn 2 of them. The R that you learned up to this point in time will be used for most of the problems. I'm going to introduce an R to you in one set of problems, okay, that we're going to see in just a moment. But we will use 2 of them, and you got to decide when you want to use 2 of them. But let's think about a gas in terms of what is actually happening inside the container, okay, or inside that balloon. We come to something called the kinetic molecular theory, or, you know, we're scientists, so we're going to call it the KMT, the kinetic molecular theory. Okay, what does kinetic mean? Energy and motion. And molecule. Molecule is a molecule. And theory is something we're going to think about this. All right, so, this theory starts with what? What is the first word on this slide up at the top? Assumptions. Okay, you know what happens when we make assumptions. Sometimes it's going to get us later, okay? And it will. And I'll talk about when the assumptions break down. But for most cases, in terms of normal pressures and temperatures, meaning that pressures that you live in and temperatures that you can exist in, okay, these assumptions work very well, okay? You need to know these assumptions. 1, gases consist of a large number of molecules in constant random motion, okay? There's where the kinetic comes in. They're moving. Volume of an individual molecule is very, very, very small compared to the volume of its container. So the actual molecules take up really a tiny fraction of the space. So that's saying they essentially make up no space. They're so small it rounds off. 3rd, intermolecular forces. The forces between the molecules, between 2 molecules, are negligible. Okay? That means the 2 atoms or 2 molecules that are in that gas don't interact. We've said this before this way. Gases behave like they're by themselves. They do not interact. They do not transfer anything between them. They don't have any attraction to each other. The average kinetic energy of each molecule, or all the molecules, is proportional to one thing and one thing alone, and that is temperature. The last. Energy can be transferred between molecules, but the total kinetic energy is constant at constant pressure. Meaning that, yeah, we said that they don't interact, but if they actually transfer energy, then it is net zero. We lose nothing. It all averages out. Okay? And so if by chance 2 atoms randomly run into each other and bounce away, no energy is lost. No energy of interaction occurs. Okay, if these things are true, we think of a gas as being this. Small little molecules roaming around inside a container, bouncing off the walls, doing their own thing. Okay? And they are in constant motion. So if I think about pressure, pressure would be then this: how often and how hard the molecules hit the side of the container. Okay? Small number of pressure means not very many hits, not moving very fast, not very heavy. Okay? And so that's what we would think about these gas molecules bouncing around in there. Just kind of pinballing around. All around. Okay? And so, in terms of temperature, the gases have an average kinetic energy or average speed that are going around. Okay? Each molecule in the gas has a different energy. And there is a spread of them. It's an average. It's kind of like a class. There is an average grade that I can describe the class, but not everybody gets the same grade. Okay, same thing as the molecules themselves. They're all moving and just a little bit different. We state that the average kinetic energy is dependent upon temperature only so that as the temperature increases, the average kinetic energy increases, or we can say the speed of the molecules increase. So if we have a gas in a confined cylinder, all right, and we can consider a couple things. Okay, we're going to consider how does the different conditions change the average distance between the molecules, the pressure, and the number of moles in the. Okay, so we're going to look at distance, we're going to look at pressure, and we're going to look at moles. All right. If I heat the gas from 298 Kelvin to 360 Kelvin while maintaining the piston in its position, so it's same volume, what happens to the distance between the molecules? Do they go up, do they go down, or is there no change if you speed them up?
The kinetic energy increases with the temperature.
Yes, the kinetic energy increases. That's exactly true. What happens to the distance, though, between, on average, between the molecules? Even though they're moving faster. Do they get bigger? Do they get smaller? Or does it not change? It doesn't change. So no change. But what about the pressure? Does it go up? Does it go down? Or does it not change? Why does it increase? Because they're moving faster. What happens to the molecules? They hit the sides more often, less often, or the same? More often. That means the pressure goes up. What happens to the number of moles? Does it go up? Does it go down? Or does it no change if I just heat them? No change. Okay. All right. Distance, pressure, number of moles. If I move the piston to reduce the volume in half, what happens to the distance between the molecules? Does it go up? Does it go down? Or is there no change?
Distance would go down.
Distance will go down because I'm compressing everything. What happens to the pressure, though? No change, up or down? Goes up. The molecules didn't speed up. They're going at a certain rate, but they're going to hit more often because the walls are closer. What happens to the number of moles if I take the volume and move it? No change. They're still in the same number. Okay, distance, the pressure, and the number of moles. If I inject more gas into the cylinder, what happens to the distance between the molecules? Does it go up? Does it go down, or no change? Well, it decreases because if you put more in there, they're closer together. What happens to the pressure if I put more inside? It has to go up. What happens to the number of moles? It increases. So we can think about these changes about what happens in the gas either through an equation, if I'm given all the numbers, or we can think of it theoretically, what would happen to the small molecules bouncing around in the container. All right. Now, we talked about kinetic energy and how fast everything's going. And so when we describe a classroom's grade on the exam, we use the class average. The students did an average this way. And so if we find the average speed of gas molecules, if you had 4 molecules that had a speed of 4, 6, 10, and 12 meters per second, then mathematically you add them all up, you divide by how many, and you would get the average speed. Those would give an average of 8.0. This is what we learned in statistics. This is what we learn how to do averages. But here is the problem with this average. This average expects a normal distribution. Ooh, what does a normal distribution mean?
It means that each thing is equal parts.
Yes, if you take the average, there will be 50% on this side and 50% on that side. A lot of times, groups of things will distribute normally. Okay? But if you look at the top, we have something called RMS speed. It's a little bit different. All right, the speed that we're going to call is U. The normal distribution would have exactly half on one side and half on the other. But what we find for gases is that it is not normally distributed. One side gets more than the other. Which side gets more? The slow side or the fast side? The fast side has more molecules. The slow side has less. So if I take an absolute average, okay, I misrepresent the total speed, the average speed, a best fit to what will be the average, because I've got more fast ones than I have slow ones. Okay? So what I have to do is do a different calculation. And the different calculation is called root mean square speed. Okay, I take every one of the speeds and I square it. I add them all up and I take the mean or the average, and then I take the square root of that number. If I redid the calculation with these 4 values, the root mean square speed is 8.6. It accounts for gases being a little bit more on the fast side when we do this calculation. Now, when we calculate root mean square speed, will we ever have to do this calculation? Okay, what if you had a mole of gas? How long would it take you to do that calculation? You would have to know every individual speed of every one of the 6.022 times 10 to the 23rd atoms, square each of them individually, divide it all out, and then take the square root. That is ridiculous. Okay, so there's another way we're going to get to this number, not using this simple math. We're going to use a different math. It is just as simple, but it will create the root mean square speed. Now, if I think about this, energy, E, is equal to some sort of average. And if you actually did physical science or physics, 1/2 times the mass times velocity squared is the calculation for energy, kinetic energy. Here, 1/2 times the mass, we're going to use the root mean square speed because it's a gas. We're going to use that particular velocity. And so if you look at this equation, 1/2, it's a constant, mass, okay, of your molecule, and root mean square speed. If energy goes up, which is the only variable that can go up? If you change the energy, did you magically add mass to your atom? No. Did you increase the half? No. The only thing that can change in terms of energy, this is mathematically, we relate. The speed of the molecules are directly related to the energy of the molecules. This is, we've already said that. Here's the math that shows it to us. Because we can't change Just because they're fast, they don't change the mass. Okay, and so root mean square speed. Okay, as the volume increases at a constant temperature, the average kinetic energy of the gas remains constant. That means the speeds remain constant. And if I increase that volume, then the molecules must travel further to hit the walls, and therefore they hit them less often, and pressure is lower. If the temperature is increased at a constant volume, they speed up, they travel faster in the same space, they collide more often, and the pressure increases. So here's how we're going to calculate root mean square speed. 3 times r times t divided by the molecular weight. Now, wait a minute. Here's where you got to watch out. This is where we use the different r. Okay? Because we need root mean square speed, we need speed, meter over second. Well, there's meter squared and there's second squared, and oh, check this out, we do a square root. We get rid of the squares. So what do we have to cancel out? We have to cancel out temperature, we have to cancel out moles, and we have to cancel out, what is that? Kilogram. When you do a molecular weight on the molecular weight calculator, what unit do you get? Grams per mole. The molecular weight must be in kilograms per mole for this to work. So you have to use a different R, and you have to use a different molecular weight. Okay? Do you know what's going to be really, really bad on the exam if you use the other R and you use grams per mole? Lo and behold, you'll have an answer that matches up. It will be completely wrong. Okay? CHEM-111 will let you get around that. Okay, you got to do it absolutely perfectly right. But this is where we use this R, and you have to change the molecular weight. You have examples of this in your homework. But this is what I wanted you to do. So the constant 3, this new R, the temperature has to be in Kelvin, and the molecular weight has to be in kilograms over mole. Most often, people miss this on the exam. They will not put kilograms per mole. They will get an answer, they'll bubble it in, and they feel very confident about that question. Okay, don't feel very confident. Actually use the units, see if they actually cancel out. If it cancels out, it may help you know that you're on the right track. If you never use a unit in your calculations, it's an assumption you're making, and you know what assumptions can do to you. Okay. All right. Now, here's a kind of a question I might ask you. Given 2 molecules, or given a list of molecules at the same temperature, which ones are faster? Okay? You don't even need to do the actual calculation. You don't even need to do a square root. Okay? You can line up 10 molecules in order of their speed, the fastest to slowest, by looking at one number only. And what is that? Not the temperature, because temperature is constant. All of them. The molar mass. Which ones go fastest? The smallest. Which ones go slowest? The largest ones. Okay? Given the constant amount of energy, if you got a big old semi, if I'm pushing a semi, it's not going to go very fast. But if I push a little mini, I might be able to get that going some. Okay? And so you can do the ordering of the speed without actually doing the calculation of the speed itself. Graham's law of effusion. Okay, effusion is this. If by chance there is a little tiny hole and a gas there, okay, the gas will get through that little tiny hole, okay, and if you have 2 gases, the one that has the smallest weight will go out faster. Okay, it's like this. Have you ever bought a balloon that had helium in it? Right? And you bring it home and it's up at the ceiling and it's nice. And then what happens overnight? That balloon kind of falls down, and what do you have to do? If you cut off the string, it goes right back up. and then the next night you cut off all the string and then just kind of, what's happening? Okay. There are little tiny holes inside your balloon. And what happens is the helium is effusing through those holes. Now, there could be helium in there, but it might not be pure. Some argon sometimes gets in there. Okay? What happens is the helium is moving around so fast because it's got very little weight. It's bouncing around, and it hits the sides more often. If it hits the sides more often, there's more of a chance for it to hit the hole and come out. All right, that's the main reason why the faster it goes, the more times it hits, the more chance it's going to hit through that hole. Also, if it's smaller versus a larger gas, it has more of a chance to fit through the hole. That's a smaller part of it. It's mainly due to its speed. Okay, and so smaller gases effuse quicker than larger gases. Okay, that's a concept. Diffusion. Okay, diffusion is the spread of a gas through space. It is dependent only upon its formula weight. It's faster for molecules, and so it is significantly slower than the root mean square speed, okay, but it is pretty fast. So if you open a bottle of perfume, all right, if I open up the top of a perfume bottle, over time you should smell that, okay, or let me say sometimes there are freshman girls and freshman guys, or oh, let me tell you, this is where it is. Middle school guys. Okay? Yes, what is it? The axle. You can smell them before they round the corner. Okay? Because they won't take a shower, but they will use axle. Okay? Because the commercials say they're going to get all the girls, right? And so if they use a little, they'll get a few girls. If they use a lot, middle school guys. Okay. All of that molecules are effusing. All right? So let's do this. Let's calculate the speed of bad breath. Okay, let's try that. How in the world will we calculate the speed of bad breath? I'm gonna actually go ahead and add a brand new slide so I can do this. Okay, we're gonna do the speed of bad breath. No, done. All right. So what do you exhale? What gas? Carbon dioxide. CO2. Okay, carbon dioxide is 12 for carbon and 32 for oxygen, 44 grams per mole. Okay? All right. And so that is cool. All right. And so if I calculate this, all right, the root mean square speed is equal to the square root of 3RT over formula weight, or molar mass. All right, here we go. I'm going to do this. The square root, 3R. Someone look up that R. It is 8 point what? 3 what? 1 4. What is its units? What is it? Kilogram times a meter squared divided by a second squared times a what? Mole times a Kelvin. All right. How hot is bad breath? Do you know?
Would be like your body temperature?
Your body temperature, which is approximately 37 degrees Celsius. Okay, plus 273.15 is 0.15 Kelvin. Okay, 3 plus 7 is 0. Carry the 1. 7 plus 3 is 0. Plus the 1 is 11. Carry the 1. Okay, that's your temperature, body temperature. Okay, and the formula weight is 0.044 kilograms per mole. All right, I'm going to need somebody to do some math for me. Mole, let's cancel out. 3 times 8.314 times 310.15 divided by 0.044. Oh, wait. I'll get the square root of some number. Who's got the number inside there? No one? Anybody?
419.
Oh, 419, that's after the square root, correct? Okay. All right. So 419 meters per second. That's after the complete square root. Okay, that's u. All right. How fast is that? Do you know how fast that is? Not really. Okay, so let's put it into something that you know. Meters per second. Okay. Seconds can be converted into minutes. Minutes to hours. Okay. So what? 60 seconds, 60 minutes, 1 hour. Okay, now I've got meters per hour. Well, that doesn't mean anything to me. Okay. In this case, meters to centimeters, centimeters to inches, inches to feet, feet to miles. All right. 1 centimeter, 1 e to the minus 2. Okay, inches. What is that one? 1 inch to 2.54 centimeters. 1 foot is 12 inches. 5,280 to 1 mile. Okay. That's 5280. All right, let's see what happens here. 419 times 60 divided by e to the 2, okay, divided by 2.54, divided by 12, divided by 5,280. No, that doesn't look right. What did I get? What was wrong? 419. Did I get it right? Meters, 1 centimeter is that. 1 centimeter is this. Inches, 12 inches is 1 foot. It's 1 mile. 419 times 60 times 60. Okay. Divided by 0.01. Okay. Divided by 2.54. Divided by 12. Divided by 5. Yeah, that looks nice. Did anybody else come up with this? 937. Oh, that's how fast your bad breath is coming at you? That's fast. That's really fast. Okay? That's way too fast. Brush your teeth. Okay? All right. Now, the perfume's coming at, I said the perfume is coming at you at about 900 per hour, right? 900 miles per hour. This was 937. Why in the world does it not immediately hit into you? That would be the speed in a vacuum, okay? Where the molecule just travels straight line from me to you. You'd be able to, it'd hit you in your face pretty fast. Here's what happens. Molecules do not follow a straight line because the molecule will go for a little bit and all of a sudden it will hit a nitrogen molecule and then it deflects. Okay, it can deflect up, down, side, and it'll travel a little bit and hit another molecule, and then it deflects. And so your molecules will travel at 900 miles per hour, but eventually it's got to travel and it will get to you. This is called the free mean path. How far does it travel before it hits something and gets deflected? Hopefully, your free mean path in a car is farther than 6 times 10 to the minus 6 centimeters. Okay? And so it bounces around like a pinball through all of this atmosphere to actually get to you. But it's traveling at a very high rate. That means if it takes a little while for you to smell something, that meant it traveled a very far path to get to your nose. Okay? And so the free mean path is the distance that a molecule will travel before it hits something else. At sea level, that's where the densest part of the atmosphere is. It hits a lot of things. If you go to the top of a mountain, it will actually travel a little bit farther before it hits things because there's not as much material there. And so the free mean path will increase as the material decreases. All right, the real gas. All right, if you have 1 mole of any gas, then if you take the pressure times the volume divided by RT, you should equal 1. But in a real gas, if you take the pressure, the volume, the R, and the T, and you take those measurements, those 3 measurements, and you do the calculation, it doesn't equal 1. Okay? We've been working with what's called the ideal gas law, but there is real, because the assumptions do not always occur. Now, why this is called the ideal gas law and why we got these gas laws was because of this. At normal pressures and temperatures, like the kinds of pressures and temperatures I get on the chemistry bench, they always worked. They always came out right. They always came out with our predictions. Okay? And so we were very confident from an early stage that they would always work. But this is where the ideal gas law breaks down. These 2 assumptions. The molecules do take up space. In the ideal gas law, we consider the space the volume of the molecules actually take up is 0. They actually don't take up space. And then we do our calculations. Also, the molecules do interact with each other. Okay? And so if by chance I take a gas and it's in a very large volume, the actual molecules are so small that they are almost nothing. But if I decrease the volume to little tiny, tiny, tiny volumes, the size of the molecule never changes, but the actual percentage of the volume of a very tiny space will actually be part of the molecules themselves, and I have to correct for it. Okay? If it's in a big volume, don't have to correct for it. It rounds off. But if I'm in a very tiny volume, the actual molecules take up space. So I have to correct for volume. Well, how do I get volume small? 2 ways. High pressure, meaning that it gets squeezed down. They start to act like real gases. Or cool it down. Very cold temperatures. Remember, as the temperature decreases, the volume decreases. So if it's under very high pressure or very low temperature, either one of those, I will have to account for the volume of the molecules themselves. Secondly, the molecules, gas molecules at normal temperatures, relatively high temperatures, are moving so fast that they go past each other so quickly that they don't really interact at all. But if you slow them down or put them close together, then the molecules will take up more time interacting with each other, and so their interaction changes their behavior. How can I make them go slower and interact more? I cool them down, okay? They get small volume and they're going slower so they have more time to interact, or I put them under high pressure, meaning that they're really close to each other. Then they have to interact. So I have to adjust for how much pressure is there. If it's under very, very high pressure, under very, very low volumes, I have to really account for these. Okay? And so I have to account for the volume and the pressure. This is important. You need to understand why we actually make the adjustments. And then I'm going to show you mathematically how we do that. Van der Waals equation. It is PV equals nRT, but it's got a couple things. All right? Right here. This adjusts for the interaction, how the molecules interact. It's related to how much pressure is there. So this will account for that. And it accounts for it in two ways. It's got, if there's lots of moles, that talks about interaction. And if the volume is little, that talks about the interaction. And here is an experimentally derived number that is unique for each gas. So each gas has its own A value. Also, I have to correct for volume. And so if it's very, very tiny volume, then I have to have a term called B, and that's also related to, you can have a little tiny volume, but if you have a little tiny amount of moles, it doesn't have to be corrected a lot. But if you have a really tiny volume and have a lot of moles, then you really have to correct for it. So the B term is the correction value, which is also related to the number of moles. And so it is P times V, but you have to adjust P and you have to adjust V so that the gas equation will account for those oddities when it behaves like a real gas. This is called the Van der Waals equation. Okay. Now, the A and the B value have to be experimentally derived, and there are tables of these for each gas known. And so the A has really weird unit, liter squared times an atmosphere divided by mole squared, and the B has a unit of liters divided by mole. You would have to be given this or look it up in a table to use Van der Waals, okay, equation. And so if 1 mole of an ideal gas were confined at 22.41 liters at 0 degrees, it would be expected to exert 1 atmosphere of pressure. But if you change this for the chlorine, it changes it just slightly off. The colder it gets and the smaller volume you have, the deviations become larger. Okay? If you do it at 22 liters and only at 0 degrees Kelvin, there's essentially almost no difference because the volumes are so large and the temperatures are so hot, relatively. Even 0 degrees Celsius is hot. It has to be negative degrees Celsius pretty substantially, and the volumes have to be very, very tiny for Van der Waals to really change the calculation. All right, how do you know when you have to use the real gas law? If the problem says it is a real gas, you use the real gas law. If it doesn't say real, then you use the ideal gas law. So that's when you know you have to use a real one, when it says real. Okay? Or they may use a question like this, where you calculate both the ideal gas law and the real gas law. But real will be in the problem, because it's a real problem. All right, that is the end of the lecture material. Let's take a look real quick